Welcome to the Design Make Play Show. I'm Sarah and I'm an illustrator and designer at Zen Maker Lab. And today we're going to talk about the different programs that we can animate in, and I'm going to show you guys a short little demonstration of how to animate in Procreate. So let's get started. So what is frame-by-frame animation? Well, it is the traditional method used in all animation, and it's the technique used to create the illusion of movement through incremental changes between each keyframe. And I'm going to show you guys what that looks like so we get a better idea, and I'm going to show you some methods of animating. So I'm going to dive into my presentation here. So to start with, this example is showing this turtle moving frame by frame in incremental changes. So what you're seeing here is the start pose is the keyframe, this middle pose is another keyframe, and the ending pose is another keyframe. So frame by frame is between those keyframes, showing this character moving in motion. So for the animators, they have to draw every single movement of this character moving all by hand traditionally. So it's a lot of work that goes into this. And here's another example showing you guys what this looks like, the character moving in motion. And this example again shows a gesture and an expression of a character moving incrementally. So there's so much work that goes into this, but this is kind of the keystone of all animation, but we've advanced obviously from that point now. So I'm going to show you guys some methods of the past of animating and then to now what we've been doing in 2020. So to begin with, the first method of animating was called celluloid or cells, and this image showing this guy working here, he is drawing on cell paper, which is translucent paper that can be layered on top of each other. So everything that they are animating has to be drawn on this paper, and it's stacked on layers, and they have to do the drawing, the inking, the painting. So it's a very big process to create films like this, and it wasn't the most commonly used back then, but now it's pretty ancient, I'd say. And some examples to show you guys of what movies did this was Steamboat Willie was one of them. And then Snow White and the Seven Dwarfs was actually a very historical moment for Disney because it was the first colored cartoon and one of the last celluloid movies made, because there was so much work that went into it, and they had 1 million sheets of cell paper, so you can imagine how much work that was. And then Bugs Bunny also used this technique. So now I'm going to show you guys a YouTube example so you get a visual understanding of what this looks like. So here the characters are moving, and again, everything you're seeing is drawn by hand in incremental changes, frame by frame. And then you can see the background is stagnant. So that's what they were doing then. And then moving forward into using color and inking, behind the scenes, the women were working on different cell sheets, and they were in charge of making the different layers and drawing over top of pencil drawings. And then after that point, they would move on to the coloring stage. And Disney actually created their own color palettes, which is kind of cool. The next example is stop motion. And this is really cool because this type of animation was also used historically a long time ago, but is still used because it has a really appealing, unique look. And what you're seeing this guy, he's doing, he is moving these physical puppets all by hand. So every single little change of that character moving and his face changing and the expressions, everything, that is what stop motion is, and that person's in charge of making that character move all by hand. So again, a lot of work is put into stop motion, but again, it has such a unique look, that's why it's worthwhile. So this is one example of a movie that did this, Chicken Run, and then Early Man, and The Nightmare Before Christmas also used this technique. So I'm going to show you guys a YouTube example of what this looks like. So in this video, what you're seeing is this lady, she's carving each different expression and face of different characters. So everything they do has to be done by hand, and then they're making the entire sets by hand. There's someone who's moving and constructing the character to make them look like they're moving in motion. So again, crazy amount of work for this type of animation, but it's super cool and you can get a greater appreciation when you're watching these kind of films. And then we have 2D animation, which is kind of the mix of traditional as well as digital. So they're using the computer, but they're also drawing by hand for the characters. So one example of a movie that does this is The Emperor's New Groove. So as you can see, it's still flat, so it's not 3D, but it does have a little bit of a different look than painted. So here's another one. Hercules was an example of this, and Lilo and Stitch. And I'm going to show you guys a quick little video of what that is. So again, someone drew what this character looks like in paper, and then they bring it into the digital programs. They do all the coloring, the refinement, and then they bring it into After Effects to do those special effects and really work on the lighting and the mood of the animation. So the last animation method I'm going to show you guys is 3D animation, and it's most similar to stop motion animation because they're puppets as well, but they're actually digital puppets. So stop motion is actually physical puppets that you can manipulate, but 3D is puppets that the animators create in the screen, but they still have complete control over what they do and how they move. So there's no drawing involved like 2D or celluloid. And some example of movies that do this technique is Toy Story. So you can see that these movies, again, they aren't flat. They're 3D, so they look really like real life and that they're popping out of the screen. This is Finding Nemo. And then we have lastly The Incredibles. And I'm going to show you guys my final example. So again, everything they create in these movies, they still have to do it by hand, but it's done digitally. And these characters from Madagascar, again, were all created by hand. They have to pretty much build and construct these characters, do all the shading, the lighting from every angle so that they look like the real deal and that they're like a living object in the screen. So yeah, they're pretty much puppets, but digitally done. So those are some examples of different animation methods, and hopefully you guys have a little bit of an understanding of frame by frame and can get a greater appreciation for how animation works. So ultimately, what I hope you guys took away from today is that there's a lot of different methods of animating, and the ones we covered today, we covered celluloid, 2D animation, 3D animation, and stop motion. So they're all different in many ways, but also similar in some. So I hope you guys learned something new, and next time you're watching a movie or a TV series, you can think about a couple of these things. So have fun, and I'll see you in the next segment.
So I know that energy is being generated in the speaker and needs to be transmitted into the wine glass. But how does that happen? How does the energy move from the speaker into the wine glass? And for that matter, what is sound and how do we hear it? I know it has something to do with air. Let's investigate. Ah, nice landing. So let's go ahead now and talk a little bit about air. All right, some of the properties of air. So first we're going to talk about what air is made of. Now air is primarily made of two types of gases, okay? Nitrogen and oxygen. And actually nitrogen takes up 78% of the air around us, while oxygen actually only takes about 21%. And of course that last bit is left to other gases. Now we can see here that I've drawn air as a bunch of these little things. Now these are little atoms or molecules, and these are actually the little pieces of air that make up what we breathe and what we interact with on a daily basis. It will take up the volume of the container that it's in. Okay, so for example, imagine that we've got a room here, okay? And I've trapped all the air on one side of this room. when I open this door, the air is not going to sit on one side. It is going to fill up this entire room. Okay? And this is known as diffusion. And this is different from a fluid. Okay, so a gas will fill all the sides of the container that it's in, where a fluid, you know that it's got one face, right? So for example, if I had a glass of water, the fluid would fill most of the container except for one side, which would be exposed as the fluid. So the gas will fill up the entire container. Now, gas can be compressed and it exerts some sort of pressure, okay? It exists, it's here. And there are two things that we can do to affect the pressure of a gas, okay? So one is that we can actually shrink the size of the container that the gas is in. So here I've got a little box and there are 10 molecules in this box, 7 nitrogen and 2 oxygen, one extra. And if I compress this volume, I'm going to increase the pressure, okay? Similarly, if I increase the temperature on this box, I am also going to increase the pressure. And that's because these little particles are going to get more energy and they're going to be hitting all the walls and everything and exerting some more pressure. And we can use this principle to create pressure waves through the air, which is fluid, to create the sound that we hear. And primarily a speaker will do this by changing the volume of air. Okay, so we can see here that there are some sound waves, pressure waves that are exerting through the air in this diagram. And this is our speaker here, okay? And do you remember last time we were talking about electromagnetism? So there's a diaphragm on the speaker that's moving in and out as we change the current and we change the magnetic field, okay? We're using that property to create mechanical energy. And these waves are protruding from that diaphragm, okay? And we can see that on the pressure waves, okay, of this sound, the highest amounts of pressure, all of these little particles, all these little molecules of the air are actually closely packed together, like in this diagram. So this would be a high pressure wave. And then in between those high pressure waves, we see that there are some that are kind of dispersed. Can we see that? There's only a few. So in between these waves, this is a lower pressure, okay? And this variable pressure, if we measured it over time, it would look something like this. And this makes up the sound that we hear. Now, if we wanted sound to be louder, okay, we would increase the amount of pressure on these waves. And that would look like a higher amplitude, right? So remember, this is measuring the pressure. So as we increase the pressure of our waves, these things will get louder. Similarly, if I wanted to increase the pitch, so that is sort of, if you think about sound, we can go from a low to a high, right? That's the pitch. If I wanted to increase the pitch of my sound wave, I could actually make this thing vibrate faster and get those pressure waves to get closer together. And this would give me a higher pitch. Finally, the auditory range that we can actually hear is between 20,000 hertz, or sorry, 20,000 hertz and 20 hertz. Okay, so we will only be able to hear the pitches between these two ranges, or these two frequencies. So that covers everything that I wanted to talk about air. Let's go ahead and see these concepts in action. Glad at that one. All right. So we know that air takes up space, right? We know that it's made of these little particle things, but where's the evidence? A balloon is a great example of some evidence that air takes up space, right? Now, if this was filled with nothing, obviously I could crush it down flat, right? There'd be nothing in there to withstand or to resist my push. But as I push down on this thing, we can clearly see that it's taking up space, right? So that is actually the air that's inside is taking up the space and forming the shape of the balloon. And we can see here that if I push down on it, it will actually kind of condense and deform. So not only does air take up space, but it can also be kind of compressed. If I jab a little hole in the top of this balloon, If I jab a little one, let's see if I can do it here. There we go. It will actually come out, or we can blow it up bigger. Well, that's not really working too well, is it? Oh boy, let's see, can we blow it up bigger? So we can see that we can actually fill things with this air to take up more space. Another really great example is here, okay? So another example of the evidence of air is actually this glass, okay? So here I've got this jug, it's full of water, and in this glass there's nothing, right? There's nothing in there. But if I turn it upside down and put it into the water, we can see that the water doesn't actually fill the inside of the glass. And in fact, the glass is pushing up against me. And we see these little things that kind of come up. That is air, okay? Air is taking up the space there. And not only is it taking up the space, okay, in that glass, but air is actually less dense, so it tends to rise. So it's pushing my hand back up. It's trying to escape. It's trying to escape its enclosure here. So not only does air exist, but it's fluid, right? And so it'll take the shape of whatever kind of container it's in. We kind of saw that with the balloon when I was squishing it, compressing it. So because it's got these certain properties of a fluid, it's great for transmitting waves, okay? And this is actually how sound is made, right? Is from the transfer of energy through these waves in a fluid. Usually, you can send waves through solid structures as well, which will be more vibration, right? But we are going to now demonstrate some of these waves, or at least try to demonstrate, using a speaker. So we're going to be transmitting some sound waves through the air that are going to hit this water and generate waves like the ones you can see when I slap my hands against the surface. So for our next demonstration, and this is our last one for today, we are going to be blasting this water with some really deep bass sounds, okay? So on the lower end of the frequency that we can hear, okay, our audible range, all right? And these bass sounds are gonna travel through the air and actually vibrate on the surface of the water. And we're gonna be able to see some of the vibrations that are actually being transmitted from the speaker through the air and into the jug here. We've also got our initial wine glass right beside as well, and hopefully we'll be able to see some of these vibrations. Now, these vibrations are very prominent. If I hit the table, we can see that they vibrate quite well. But we're also gonna see how this happens through sound, okay? So nobody's gonna be hitting the table here. It's just gonna be purely sound. Let's go ahead, let's jump into it. So I'm gonna turn this guy on, and we're gonna get started here. And we're gonna turn up the volume. So that last test really resonated with me and had good vibes. Let's go ahead now and head back to the DesignMakePlay room. Oh. So we just finished a couple of demonstrations using sound and air, and now it's time for some challenge. So I hope you're ready, hope you're excited. So your challenge for this video is I want you to find a source of some sort of sound. Okay, that could be anything, but hopefully it's fairly consistent, okay? And I'd like you to use a mechanism that you can use to record sound. So that could be a computer, that could be a phone. And particularly, I'm interested in the decibels, or the amplitude that you can hear that sound, how loud it is. And what I want you to do is slowly change the distance you are from that source, okay, and measure the amplitude as you get further and further away. And tell me, what is the relationship between the source and how loud that sound is? So that is your challenge for this video. I hope that you enjoyed learning about the properties of sound and air. And join us in our next episode where we will be learning about computational thinking.
Good morning, everybody. My name is Rodney Gilbert. I'm a play instructor at DesignMakePlay, and today we have Ella on the show. She is a material engineer and also an instructor at DesignMakePlay. On the first episode, you guys went over locomotor skills and the basics of them, what they are. In today's episode, we're going to be going over locomotor skills in sport. So the sport we're going to be using to show these locomotor skills is baseball. So let's get started. All right, everybody. So the first locomotor skill we're going to go over is running. So running can be used in many different ways in baseball. But for this drill, we're going to simulate going from home to first and rounding first base like you're going to go to second. So for this drill, I'm going to demonstrate it once, and then Ella's going to go through it and show you guys how it's done. So we're going to start at home plate. From home plate, we're going to pretend like we hit the ball. We're going to start running. We're going to banana out, so go a bit wider. We're going to come back inside towards the bag, and we're going to step on the bag with our inside foot and keep running. The key emphasis is to make sure that you are stepping on the inside of the bag, because when you are running the bases in baseball, that will speed you up quite a bit. So here's Ella to demonstrate. You see how she got wider here when she came towards first base? That really helps you get the proper angle to get your foot on the inside of the bag. So the second locomotor skill that we're going to go over is like jogging, but it's sprinting. So that's full exertion of energy, full speed. So this can also be used in many different times in baseball, like also running to first base, but in this example, we're going to use it to track a fly ball. So the first step we're going to do is we're going to start facing the ball. The ball is going to be hit over our heads. We're going to open up, and we're going to full sprint back to the ball. We're going to get under it, plant our feet, we're going to catch the ball and get ready to make a throw. So this is an important locomotor skill because it's used frequently. It's one of the most frequently used, tools in baseball is sprinting to go catch a fly ball. So Ella here is going to show us an example of what it looks like. Give her my glove. All right, perfect. And the ball's hit, perfect. You're going to sprint back. Get under it, awesome. Catch the ball, that's perfect. And you see how she planted her feet when she got under it? So she wasn't still moving, she stopped, she planted her feet and caught the ball. That was well done, Ella. All right, the third locomotor skill we're gonna go over today is sliding. So sliding is used many different times in baseball. It can be used while you're running the bases, it can be used defensively to make a play, it can be used just to get out of the way if you're in the outfield and your center fielder is trying to dive for a ball. So that's it's pretty key, so we're gonna go over it. It builds off the other locomotor skills like sprinting and jogging because you have to be moving in order to slide. And it's a key tool in baseball. So a couple drills we can do for that would be you at a jogging pace and you just break down into a slide when you're coming into the bag. So it would look something like this. Another drill you can do for head first sliding would be the slip and slide drill. So everyone knows about a slip and slide, you know, summer toy. You bring one of those out, get it wet, and you practice. You can slide head first, feet first. That's a good way to get practice because there's low impact, and you get enough speed because of the water to practice, you know, whatever different type of slide that you'd like. So the fourth and final locomotor skill we're gonna go over today would be diving and jumping for a baseball. So this can be used in many different situations, usually in the infield, but also in the outfield for diving. Jumping is mainly used in the infield. So there's a few drills you can do that involve jumping. One of which would be the fence finder drill. So you stand about 5 feet away from the fence with your back to the fence. A ball is thrown over your head. You run backwards, you find the fence with your free hand, find the ball, and then you jump and receive the ball at its highest point. So that would be the fence finder drill. Another drill you can do for diving in the infield would be called the quick reflex drill. So you have a partner, they're standing across from you. You get into the ready position, As soon as you get ready, they throw the ball either to your left or to your right, outside of your reach, so you have to extend to go get the baseball. So it would look something like this. So make sure you fully extend when you go to get the baseball. That is the key to this drill. And on the fence finder drill, make sure you're actually finding the fence with your free hand, because in game, if you don't, it can get dangerous. You see people running into the fence, getting hurt. You know, nothing good happens when you don't find the fence. So that's it for jumping and sliding. What you can do for a diving drill would be called the quick reflex drill. So you'd have a partner standing across from you. They'd have a couple balls, and you're gonna jump into the ready position. And as soon as you hit the ready position, your partner is gonna throw the baseball either to your left or to your right, outside of your reach. So that makes you have to dive for the ball. So it'll look something like this. And make sure you fully extend when you're done, because that's the whole point of this drill. If you don't have to extend, then you probably didn't have to dive. So make sure you get the full extension. All right. So today we went over locomotor skills that are used while playing baseball. Some examples of those locomotor skills would be jogging, running, jumping, diving, and sliding. So I had Ella show a few examples of running and jogging. So the drills that we went over there would have been, or are, for jogging, running from home to second. The key for this one is getting on the inside of the bag when you're jogging. So how we did that was we banana curved or got wide and touched the inside of the bag. For the second drill, we used sprinting, so we tracked the fly ball. The key for this one was you sprint to the ball and set your feet. You don't keep running, you have to get to the ball and stop. So that's a key for this one, don't keep moving. The third drill we went over, or the pair of drills we went over, was diving and jumping. So we had the quick release drill, and then we had the fence finder drill. So the quick release drill is your friend is across from you, throwing you balls just outside of your extension, and you have to dive and go get them. So you get in the ready position and you have to go dive. The fence finder drill is when your partner throws the ball to the fence and you have to run back to the fence, find it with your open hand, and jump for the ball. The final drill we did was sliding feet first into the bag and head first into the bag. The key for this one was when you're diving head first, you have to extend your arms to go get the bag and cushion your blow into it. So those are the drills we went over today that we're going over locomotor skills. I hope you guys enjoyed it, and I want to see you guys next week.
So we just finished a fantastic few segments, and now it's time for our math challenge. So I hope you're ready, and I hope you're excited. So let's go ahead and dive into the catastrophe problem. All right. So first things first, before we dive into the real meat of it, I want to talk a little bit about torque. Okay. So you've probably seen the effects of this if you've ever been on a seesaw. You might have learned this in school. So torque is an equation. It's sort of like it's like a turning force. Okay. It's sort of a measure of how well we are able to sort of screw something in or turn something, right? You might have noticed that if you've ever seen somebody building a bike and they're messing around with the pedals, bikes have these really big wrenches that have really long lever arms, okay? And the reason that we've got like these wrenches with really big lever arms is because they give us a mechanical advantage. Okay, they provide more torque for the same, with the same amount of force. Okay, we're just increasing the distance, right? And you can try this at home. So just grab an eraser, a ruler, and then maybe two other erasers. Maybe grab three. You can put one in the center, and that can be your pivot. You can just take a ruler, you put it on top, and you can actually move it. You can move the ruler around. Okay, you can move where the pivot is. And then you just take those other two erasers and you find the point at which they're at equilibrium, okay? And there'll be probably a difference if you've moved the pivot over slightly, or if you've got two different, not if you move the pivot, if you've got two different masses or two different sizes of erasers that you're putting on either side of that ruler, right? You'll notice that the smaller one If you move it further away, or if you take the bigger one and move it closer, they'll reach equilibrium. Okay? So that's showing you that the torques are equal. Okay? The torques are equal. All right. But this is a very important equation. Okay? This one here. All right? So it's the distance from the pivot that a force is applied perpendicular will give us our torque. Okay? So just remember T equals F times D. All right? That, at the end of the day, just that simple equation, right? T equals F times D. And I'm sure you've done a little bit of multiplication. So, yeah. Okay, so let's take a look at our real problem here. So we've got catapult number 1. All right? Pretty nifty looking catapult. And catapult number 2. And we can see here some of the things that we talked about up here. So we can see that there's a pivot, and this pivot is actually, it's a screw. So it's like, again, I'm going to talk about the ruler. So you know on your ruler, you've got like a little hole on it, right? Sometimes maybe you stick a pencil in the hole and you kind of fling it around, right? Well, that pencil would be your pivot, all right? If you've ever like swung your keys around on your finger, right? When I swing my keys around my finger is the pivot. Okay, it's the point that the keys are turning around. It's the axis that these keys are turning around. Okay, so that is the pivot there. And then we have a force applied. And this is being applied by some big rubber band. We're just going to assume that this force is perpendicular and constant at all times. It's not the exact same at all times, but we're going to assume for this that it is, just for the sake of making things a little bit simpler, a little bit easier. Now, the other thing that we noticed, so we talked about the pivot, we talked about a force now being applied by a rubber band. The red and the orange here are both rubber bands, but we can see they're at different points. So on the first catapult, the rubber band is very low, and on the second catapult, the rubber band is very high. Okay? And we have 2 distances up here for each catapult. So distance number 1, all right, for catapult number 1 is 1 meter. And the distance from the pivot for catapult number 2 is 5 meters. Okay, so we got 1 meter and 5 meters. All right? Now the question is, which catapult has the highest torque? Okay, so which catapult is applying the highest amount of torque? Which catapult do you think has a slightly better design? Is it catapult number 1 or catapult number 2? Based off of the answer from this question, which one do you think would be better? And this is kind of an interesting problem that a lot of people have had to solve throughout history when we were building different kinds of catapults and trebuchets and all these really cool devices, mechanisms. These are questions that a lot of people would sit around and ask, which is the better design for my catapult? And people still ask this today. So, I hope that you enjoyed this question. Go ahead, take a crack at it. I know it seems like a lot, but when you break it down, it's actually it's a very easy question to approach mathematically. But the reason that I'm giving it to you like this is because a lot of times the math that you get in real life is encoded in a big mess of the swirly world words, okay? So like, you're not always going to get just a simple math equation in life. You're going to get somebody that comes to you with a problem. They're going to give you a lot of information. You're going to have to break that down to what's essential. So that's what you're going to have to do here. Break it down to what's essential. Okay, but let's go ahead now. We're going to dive into our engineering tributes and maker highlights, so stay tuned. our Maker Highlights. Now this is a segment of the show where we get to highlight some really cool projects that have been worked on by students here at DesignMakePlay or submitted to us by makers around the world. And today we're going to dive into two really cool projects. So let's go ahead and take a look. So first up we have Francesca's BFF. So this project, I liked this one because Francesca is making this for her BFF. So I thought that was pretty cool. And it's something that I really like to see in projects. Again, that altruistic thing of how can I make somebody's life a little bit better using the things that I know how to do. So that's what Francesca's doing. She's making a cool gift for her friend, letting her know that she cares and that she's her BFF. So very cool project. I really liked this one for that reason. But Francesca, awesome job. And next up we have Miles Castle. And this one was pretty cool. It's pretty technical. So let's go ahead, let's take a deep dive into Miles Castle. Whoa! So this castle was actually constructed by Miles, all using basic shapes. And we can kind of break things down and see a little bit about how we did it. So let's go ahead and we can duplicate some of these parts. And we can take a look. Let me see here. I can duplicate this one. Look. We can see that the level there is actually just repeated. So he just wrote that with the scribble tool, and then he's repeated it a bunch. And again, that's taking advantage of the duplication tool, right? These flags are made out of some flat boxes and some roofs that have been sort of stretched out. Again, very cool. These sticks are just cylinders, okay? Again, elongated and made the right color. These are just some cylinders that have been actually cut away. So first we cut them hollow and then we cut a little door out for them. So that's pretty cool. The surrounding, I guess you could call them like the teeth of the castle, the pieces on the top there. These are all just boxes, right? These are all just boxes. Again, we've got sort of a flat cylinder for the inside of this very cool pillar here. We've got a door which is made out of, I believe, it's just some spears and a box. But that was pretty cool, pretty effective looking for a door. And then I really like these trees. They're pretty simple, but they add kind of like a nice touch. And those are, again, just a cylinder and an ellipsoid. So I really like this project, again, because Miles is taking advantage of the duplication tool. So he makes one part, and then he uses it all over the place. And those are some of the best designs, are these designs that are kind of modular, and you can reuse assets all over the place. So really great job, Miles, on your castle. So that covers our Maker Highlights. Unfortunately, we don't have time for our engineering trivia today, Xishan Wu, but I'm sure we'll have time for her next week. Without further ado, let's go ahead and dive into our interview for today with John. Welcome.
Welcome back to the Design Make Play show. Today I am very happy to have our special guest, John Omelianiuk. Thank you for coming on the show. John recently started here as a Maker Lab and he's been an awesome addition. Really cool background, you're already made a big impact. Today we're going to talk a little bit about, first of all, your background and everything, and then we'll get more into the whole design process and some of the considerations for that. So why don't we start with your background? Whereabouts did you grow up? What school did you go to? Interests, all that kind of stuff.
Right on. So I actually grew up in Northern Ontario, up in Thunder Bay, where it's cold most of the year and quite depressing. That's not true. Went to a school called Sir Winston Churchill High School for most of high school. I was very into band and programming. Got into programming in grade 9, making a ton of video games, just platformers and stuff like that. Somewhere about near the second half of high school, I got into robotics. Our robotics team formed, I think, when I was in grade 11, and they needed a mechanical designer. And I had no idea how to do mechanical design, but no one else would do it. So that's what kind of started that. After high school, I moved to Waterloo, took a degree in mechatronics engineering because it had a little bit of everything. It had some mechanical, it had some electrical, it had some software, and I thought, if I get to do all of those, that'd be pretty sweet.
Okay, so it sounds like you're quite the generalist. I like the idea that no one else wanted to do it, so you're like, hey, you set up the plate and said, I'll try doing it. So that's cool. You're from Thunder Bay, and I've been through there. It's actually really beautiful. So I know you get blue skies. Vancouver, you get a lot of rain. Thunder Bay's pretty cool place. Interesting place, no doubt, to grow up. And how's it been so far? Moving to Vancouver. Do you like Vancouver compared to Ontario?
Well, been here about a month. The environment is absolutely gorgeous here. Mountains, ocean. Like, my drive to work is probably the most beautiful drive I've ever done in my life, and now I get to do it basically every day. When I can see it, of course. It does rain a lot, and that does mean there's a lot of clouds.
Yeah. Okay. Well, hopefully you'll enjoy it here. I remember when I moved. I'm also from Ontario, and I moved out here and driving across the Second Arrows Bridge and seeing the mountains. I was kind of blown away too, and so I can relate to what you're saying. Mechatronics at University of Waterloo. I hear that's a really tough program. Was it tough to get in? Was it tough to do the program? You survived, you made it out of the program. Any thoughts about that?
Right on. Well, the program was about as tough to get in as any other program at Waterloo. As far as I know, I didn't really check. But I got in. It was tough. Part of the toughness of it was that it wasn't as well organized as I wanted it to be. We had a lot of high quality professors. We learned a lot of high quality stuff, but because mechatronics as a field is reasonably new, last 20 years or so, we've only had a few generations of classes graduate up to this point, so they're still trying to figure out the order in which to give us this information. So sometimes we learn things out of order, and that kind of caused some confusion. But
yes,
one of the great things about going to Waterloo for school was kind of how open they left a lot of the projects. They really encouraged mass creativity, right from scratch. And I know about this when I talk to other engineers who went to other universities. They talk about their final projects, their capstone design project, where they had to design something, and a lot of the time they're given constraints, they're given a guideline, or they're even given the project they have to do. At Waterloo, they just said, figure out what you want to do. You'll work with a prof, you'll tell them, they'll just double check to make sure you have enough content to work with, and just do whatever you want.
Wow,
that was super cool.
Well, it sounds really interesting how it's kind of cross-disciplinary with mechanical engineering, electrical engineering, and all those different elements. Now, do you think our schools, and it's interesting about your comments about the sequencing, do you think schools are moving more in that direction of sort of openness or cross-disciplinary kind of studies, or are they kind of getting more specific and sort of granular?
Right. I don't actually know if I can answer that question.
Okay.
I've been through school once, and I haven't been back to school since.
Okay.
So I have my very limited experience, which is very cross-disciplinary.
Yeah.
That's because I chose a field that is intentionally cross-disciplinary. I have no idea how the other fields look, though I can comment that fields like mechanical engineering are starting to have some mandatory programming classes and a little bit of electrical engineering thrown in, simply because we live in an electrical and a programming and a software world now. So having that knowledge and having those skills is very important for getting into the tech industry.
Yeah, I see. And what was your favorite part of your program?
Favorite part of my program? I really enjoyed doing the capstone design project. I know a lot of teams found it very stressful because you have to do this huge project in such a limited amount of time. I obviously, being here, working for you, love to make things. So for my capstone design project, I found it a great opportunity and excuse to spend about 150, 200 hours in the machine shop. And I just got to pick the brains of all the workers there, try to teach myself and get some knowledge in machining, build this crate contraption that we made, and it was just a big excuse to play around and build things and put things together. So that was definitely it.
Oh, that's nice. What was the coolest project you've ever made? Would it be that one, or was there anything that you made sort of on the side, or just personal interest that's been pretty cool? I know you're involved in a bunch of other like textiles and I think is it sort of medieval cosplay, things like that, or the? Yeah,
well, one of the more like interesting ones I've ever done. Early on, I made a chainmail shirt from scratch when I was 13, I think.
Oh wow.
Basically, I would buy all these 100-meter spools of galvanized steel wire from Canadian Tire and wrap them around a rod and cut them up, and it took way more hours than I'm willing to admit. But you know, as a kid, sometimes you don't have anything better to do, so I linked all the rings individually together and I made a shirt out of it.
Oh wow.
One of my absolutely coolest ones though is probably the capstone project. We made a big table for playing like Dungeons and Dragons on, where there's an electromagnet underneath the surface, and it moves around and it drags the pieces on top. So if you've ever seen Harry Potter, it's kind of like wizard's chess, except that you put your own like D&D figurine on top on a little piece, and it moves it to the square you want, and you can pull out your phone. And we had a really talented software engineer help us write an app for it, so you could like change your location and it would queue up a sequence, grab your piece, bring it there, and it was actually kind of magical seeing the pieces just move around on the table on their own.
Oh wow, well that sounds very fun to watch and interesting one. Now we have a lot of some of the viewers are in high school thinking of getting into possibly an engineering school. What would you recommend for like some of the viewers out there? What would you recommend that they focus on? How would they, if they want to get into a school kind of like what you did, any advice you give them?
That's an interesting question because the admissions rates for most universities are almost exclusively based on marks, which I think is rather unfortunate because especially nowadays, it's really hard to tell the level of passion and engagement you have and what your actual skill set is based on your academic marks, because schools, the whole process of marking people just with written tests and based on the curriculum they give, it's kind of shallow. The University of Waterloo was interesting in that they gave us a supplementary form to fill out when we were applying for a program that was everything other than school. Like they got our marks, they know what the numbers are. Now they wanted to hear what projects do you do, what teams are you part of, what makes you a good fit for this program, because of everything that's not related to school. And I think a lot more universities should be doing that, really looking at, you know, what does this person do? Like, do they have half a decade of woodworking experience that could translate into design experience, knowledge of using tools, passion for simply fabricating things and putting them together. So best way to go about it, besides obviously keep your marks up because that's the literal barrier you have to pass to get into university, do what makes you happy and follow it. You're gonna do yourself no favors by getting into a program because it's prestigious alone or because it requires high marks to get into if it's not something you want to do. And if it is something you want to do, you're going to have zero problems.
Yeah. Okay. Well, that's good. So, all of you youth at home, make sure you keep your grades up, do the academic side, but also don't forget about those side projects. Those are the things that I know when I'm looking at people that come to DesignMaker Lab, that's what catches my attention when they've said, "Oh, I built this or did that or this is my hobby," because that really makes things interesting. So, beyond the books. Well, since you did mention about designs and tools and equipment, maybe we'll just pivot a little bit and I'll ask you some questions about the design process. You've already made some cool things here, and one of the, is there like a certain framework that you use when you're designing something from scratch? Is there, are you just kind of winging it? Is there like a process steps you go through? How can the viewers learn a little bit about starting from scratch, designing a project? What are the steps?
Great. So there is a framework that most engineers use called the engineering design method. You do not have to follow it rigidly and to a T. They will teach you to do that in school because it's an easy framework to like mark you by, and it is a good framework to start and do design. It is very rigid, and you can take from it what you want in order to get your design done. But loosely, it looks something like this. You have to start out by outlining what the project's supposed to do. What's it supposed to achieve? These are called your constraints and criteria. One are things you must have, one are things you'd like to have. But you really just have to define in words, what do I want out of this? Next step is to do brainstorming. This is light sketching, throw all your ideas onto paper, bounce them off someone, catch them again when it bounces off. Just go wild. This is one of the loosest and most fun steps because you don't worry about the numbers, you don't worry about too much of the specifics. You just say, how can I meet these sort of needs and wants that I have, and what are the most creative ways I can do it, and how can I just sketch things out and come up with ideas to get that going. Following that, you then take these ideas you come up with and you want to select some number of them based on how well they meet those needs and wants. And one of the steps you can do to very formally quantify which one you want is to start using certain decision-making processes, which can sometimes get a little bit complicated, to narrow down your selection. In the end, you will find one of these designs works better than the others, and you'll use a variety of ways to do this. You could use the very technical weighted decision matrix, or you could simply say, or you could rationalize it out even with your coworkers. Say, this one meets it better for X, Y, and Z reasons. None of the other ones do this. I don't think there's much of a contest, so we don't have to get too technical with it. And then the final step is to work out the specifics. Now you go in, how long do I need it? How heavy do I need it? How much force can it hold? Does it actually follow the motions I need it to? That's when you get into the real specific pinpoint details.
I see.
And that's basically it.
Okay, well that's a very thorough answer. Thanks for that. Now, what about, is it better on your own to design something? Is it better to have a team of people? Like sometimes you think that, they have the expression, too many cooks spoils the broth kind of thing. So if you have sometimes, different idea, too many people. On the other hand, the lone wolf doing their own thing might miss a lot of things. So how do you balance that individualism versus team input?
I don't think it's ever a bad thing to have more people on your team, even if they're not literally involved in all aspects of the design process. Especially for the constraints and criteria and the brainstorming sessions, the first 2 phases, it's really helpful to have people to work with ideas because different people think in different ways. We're simply wired and biased and trained based on the experiences of our lives to think in certain ways that appeal to us and that we found successful. So you can find yourself very in like a narrow frame of mind if you only ever do work on yourself. When it comes to actually implementing the design, it all depends on the scale. If it's something small, you can probably do it yourself. Small CAD model, small amount of calculations, it doesn't have to be big. But if it's something big that you can separate into multiple parts, have more people on your team and scale it proportionally based on how much work has to be done.
Okay, what about the number of people? I always wonder, what's the ideal number of people to have on a team, if there is such a thing? I guess if the team gets too big, then you got communication problems. If it's too small, maybe you lack resources. For you, is there an ideal team size when you're doing some of your projects maybe in university?
In university, we worked a lot in teams of somewhere between 3 and 5, depending on the project. I know my capstone design project was 4 people, and that worked out super well. For that one specifically, it kind of scaled so that the number of people were based off the number of roles we had to achieve. So making an electromechanical system, we needed someone who knew mechanical design reasonably thoroughly. That was me. We needed someone who knew electrical reasonably thoroughly, someone who was really good at software, and then we had a third person who kind of bounced between and helped the different sections because there was more work than any one section could do alone. They could use an assistant, but they didn't want too many people sort of fighting for control over the main idea. So that team size worked out super well.
Okay.
And it all depends on how big your project is.
Yeah, I guess if you're building an enormous bridge or something, you're going to have a giant team, but I guess probably even behind big projects, ultimately the core team may be smaller behind on design side. We just have, I guess, about 5 minutes or so. one thing I'm wondering is, how do you design things, or how important is it to understand equipment and fabrication process and manufacturing when you're a designer? Because sometimes it seems like a designer makes something, they kind of throw it over the wall, and then some person who's actually making it, and they may not, they might give things that are impossible to make or very hard to make. What would you do for, how important is it to know like the equipment, the tools, the fabrication side as well?
Right, very important. I'm very passionate about this topic specifically. As a designer in university, I was what I consider pretty ahead of some of my peers, especially by the time I got to fourth year, in terms of practical and reasonable design, simply because I did work with all the tools myself. I did machining the machine shop, I did some amount of woodwork, I had some experience just in designing things for practical purposes, for costume design and sewing. So when it came time to actually design our capstone design projects, knowledge of what I could do with the fabrication tools available guided the entire process, and we had almost no problems in manufacturing it. Knowledge of what you can do with fabrication processes is so huge, and I think that's something that's actually lacking in a lot of university programs. I think any mechanical design university program, for example, should make some kind of machine shop or practical fabrication course mandatory for the first 2 terms. Get people into the shop, get people with their hands on the tools, get them to know what these tools can do. Otherwise you end up with people trying to put holes where you literally cannot fit a tool, and they go to the machine shop and the machinists tell them, we can't make this. You literally, there's no tool that can do what you want it to. So yeah, I think it's extremely important.
Okay, well that sounds really good. There's a local founder of a tech company here, Creo, and the CEO is Dan Gelbert. He's got a really good course on YouTube, fabrication on, and he had the same philosophy. He's saying like, no matter what your degrees and your technical ability, you got to get right in the machine shop and learn the basics kind of thing. Well, that's really good. I think we're pretty well run out of time here, but thanks so much for joining us, John, today. And you've got a wealth of knowledge, and at a young age, really cool projects you're making already. And yeah, hopefully we'll get you back on the show in the future sometime to get into another topic area, but this was just an introduction to get to know you a little bit and learn a little bit about the design process.
Perfect. Well, thanks for having me on, Terry.
Sounds great. Okay, well, thank you everyone for joining us today on the Design Make Play show. Hope you enjoyed it, and we will see you tomorrow. Take care. Have a nice day.